In Chapter 4, we'll be looking at reactions of alkenes and alkynes. So in the last chapter, we looked at naming different alkenes and a couple of different mechanism type arrows that will show us how the reactions work. And in this chapter, we're going to specifically look at several reactions. The picture that you see here is a military person wearing a bulletproof vest that is made of Kevlar. And Kevlar is a high molecular weight polyethylene polymer, which means that it is made up of several alkene units using alkene chemistry. Some of those reactions we will see in this chapter. There are several reactions that we can do with alkenes. They are very useful to react as nucleophiles with different electrophiles, and we get useful products by addition of these. From an alkene, we can make an alcohol, we can make an alkane, we can get a diol, which has two alcohols, carbonyl compounds. We can make cyclopropane, which is a three-membered carbon ring, an epoxide, which is a three-membered ring with oxygen, a halide with an H and an X, or a dihalide, and also a halohydrin, which contains a halogen and an alcohol. All of these reactions we can do starting from an alkene. We want to look at different types of reactions and put them into categories and help break down what each of them do. So we want to also look at the general principles and patterns of reactivity that also ties this organic chemistry together. So you want to remember the four major categories of organic reactions. So the first is the functional group transformation. We have oxidation, which is the loss of hydrogens or gain of oxygen. Reduction is the gain of hydrogen. And then we have carbon-carbon bond forming reactions. The first of the reactions is the addition of HX to an alkene, and we can do this using Markovnikov's rule. And what that says is that in an unsymmetrical alkene, so one that is like this, where it's not symmetric, this is asymmetric, this would be one that is symmetric. If you have an unsymmetric alkene, the HX reagents can add in two different ways, but one is going to be preferred over the other. If one orientation predominates, that would make it regioselective. If I look at this unsymmetric alkene, if the reaction prefers to add here versus the other side, that would be regioselective. So Markovnikov observed in the 19th century that adding HX or something like HBr to an alkene, the H attaches to the carbon that already has more H's, and the X attaches to the side that has more alkyl substituents. So that is Markovnikov's rule. In this reaction with 2-methylpropene plus HCl, we think of H and a Cl. Each of one of these things is going to go on to one of the carbons on the alkene. The carbon that has more hydrogens, which is this one, will get another one. So you can think of the H wanting to be with its friends, and it wants to surround itself with people like it. So this H goes here to go along with the H's that are already here. The chlorine then goes on to the other carbon. So this would be 2-chloro-2-methylpropane, which is the only product. In theory, you could also form the other product that sometimes people will write is that the H goes on to this and the chlorine goes here, but this is not formed. This reaction is regioselective. The halogen prefers the more substituted carbon. The H prefers the carbon that has more H's. This is a regioselective reaction, and it goes according to Markovnikov's rule, which states that H adds to the carbon with more H's. So in the addition of 2-methylpropane, which we just saw, there's 2 alkyl groups on this carbon. There's no alkyl groups here. We add HCl, The H goes to the carbon with more hydrogens, and this Cl goes over here. When it's regiospecific, one product forms where two are possible. In this reaction here, we're adding HBr. So one carbon will get a hydrogen, the other will get a bromine, and we're going to look at the substitution pattern. There's one H here and one alkyl group versus two alkyl groups. This one has less, so the H is going to go to that carbon. And the Br will go to the other carbon. So we get one bromo, one methyl cyclohexane. If both ends have a similar substitution, then that reaction will not be regiospecific. In this case, it's a symmetric molecule. This one is not regiospecific. We can look at another example of that, where on both of these carbons there's only one alkyl group. There's an alkyl group here, there's one here. There's not going to be a large preference for either one. There are more carbons on this side, but the substitution of that alkene is the same. So this one will not be regiospecific. We can get Br here or on that one. If we look at this example again, this is going to do a proton transfer. And the carbon with more hydrogens will get the hydrogen. And when this pair of electrons goes to get that hydrogen, this is now deficient and will be positively charged. And this is a tertiary carbocation. So we have 3 carbons coming off of this carbon with a positive charge. So this is a very stable carbocation. Our Cl- is going to act as the nucleophile. This is our electrophile. And we're going to get a nucleophilic hug. That to go there. So we get the addition of Cl and again get 2-chloro, 2-methylpropane. So if I do a mechanism here where we get the proton transfer, and let's say our H adds to this here, our carbocation would then be here. So if the electrons loaned itself to making a bond with this hydrogen and it went to this one, this would now be deficient. This is a primary carbocation, which is unstable. And the stability is based on how many groups it has around it to support that positive charge. In the tertiary, it had 3 carbon groups that can lend its electron density in to support that positive charge, but with the primary, you're not going to see that. So this is unstable. So we are not going to see this happen. In this reaction with the methyl cyclohexane, we're going to see the same type of mechanism. We're going to get a proton transfer. So the hydrogen is going to go to the carbon with more hydrogens. That will be here, which means this carbon becomes positive. So this is the transition. We have Br- that was kicked off from here. This is our nucleophile. This is our electrophile. And we're going to do a nucleophilic hug. And we add bromine there along with the hydrogen here. So this again is going through this one also is going through the tertiary carbocation. What we won't see is the primary carbocation forming. What we won't see is the other carbocation forming. This one goes through a secondary carbocation. and this is not formed. If we look at carbocation stability, the methyl carbocation is the least stable. It only has hydrogens around to support it, which are not very good at holding that electron density. This is a primary. Secondary, which has 2 carbons. The carbon positive here is the carbocation, and it has the support of the 2 R groups. This one is tertiary. And the stability trend moves this way. The increasing number of alkyl groups to support the positive charge makes it more stable. And that is due to the vacant p orbital, and when that positive charge is there, it can lend its electron density into the carbocation to support the positive charge. If we look at a couple of reactions here, we, in addition of HBr, can start by drawing the carbon chain. The H is going to go to the carbon with more H's. Here we have 0 H's, this has 1, so it will go here, and the Br will go to the other. And that reaction with Hi will be similar. H will go to the carbon with more H's, which is the end carbon. H will go to the carbon with more H's, which is the end carbon, and the iodine will go to the more substituted carbon. The next reaction is a hydration reaction where we add water to an alkene. So we're adding water, or HOH, to give an alcohol. And a lot of times we need an acid catalyst to make this reaction occur. If we add ethylene, which is the 2 carbons plus water, we get an OH plus H, or ethanol. So the phosphoric acid here is a catalyst. So the mechanism of how that works is very similar to the HI, or halogen addition. So sometimes it helps to write water out that way as HOH. The first part of the mechanism is a proton transfer, so a plus minus H. So 1 carbon gets the hydrogen, and these are both symmetric. This will be a positive primary carbocation, which is not super stable. We have OH minus sitting around. This is our nucleophile, electrophile, and this is a nucleophilic hug. And it forms the alcohol. This is also a Markovnikov addition. So if you did a reaction with water with an acid catalyst, so H plus can represent acid, with an alkene that is asymmetric, the OH would go to the more substituted carbon, and the H goes to the less substituted carbon. So you can look at these reactions and try to identify what the products or the starting material will be. In this first example, we have a symmetric alkene. So it doesn't matter which side gets the H or gets the Cl. Both of them will be equivalent. These are the same. The next example is asymmetric. So we have to make sure that the hydrogen goes to the least substituted, our OH goes to the more substituted. In this example, this should be HI. An iodine was put here and it's going to the more substituted carbon. So the alkene that we would have before this could be this one, where the I gets put here and the H there, or you could put it there. So both of these alkenes would result in that product. Here's a couple more problems. We're going to add water across the double bond. This is an asymmetric alkene. H goes to the one with more H's. We get the OH addition here. H goes to the carbon with more H's, which is this one. That one has 0. This is where the OH goes. And if we try to figure out what alkene goes here, it could be this one or that one. We can also add halogens to alkenes. You think of that as ClCl. So 1 chlorine gets added to each of the carbons. This is 1,2-dichloroethane. So bromine and chlorine add to alkenes to give 1,2-dihalides. So this is used a lot in industry. Using fluorine is too reactive. And I2 does not add. That one would be too slow. So chlorine reacts similarly to a Cl plus and a Cl minus, and so does Br. So these two, the chlorine and the bromine, can polarize themselves and send their energy to making one end nucleophilic or slightly negative, and the other end will be slightly positive. So if we imagine our alkene here, we imagine our alkene. This one is slightly positive, this is slightly negative. This is nucleophilic. So this electron pair can come up here, and that kicks these up to there. And then those electrons are also coming down at the same time. So this Br is positively charged. This is called a bromonium. Plus Br minus. So any reaction with something like cyclopentene or an alkene, what we're going to see as the product is the trans 1,2-dibromo cyclopentane. This one is not formed. So the addition is trans. So this, we get a nucleophilic attack here of the Br. We saw in the last slide that we formed a bromonium. That's an intermediate. We have another Br floating around here. This is an electrophile. It's a very good electrophile. This is our nucleophile. We have a 3-membered ring strain here and also a leaving group. So this nucleophile is going to come in from the back end or the underside of this one and bring the electrons up to there. So that one got kicked off and got its electrons back. And then we have this Br that came in from the underside. So that's how that one would work. So what we want to look at next is what we would expect to obtain from addition of bromine to 1,2-dimethylcyclohexene. So 1,2-dimethylcyclohexene is cyclic. We have an alkene, 1,2-dimethyl, and we're adding Br2. And we should expect a trans addition. So one of these methyl groups will be up, the other one is going to get pushed down. So this bromine has to be down, and that one is up.